Now, let's summarize what we have and let's use Simulink to verify numerically what we have found. So, what we have is, we have considered a first order linear system of the form x dot equal to ax plus bu and y equal to cx plus du. And we have found that if c times b is equal to 0 or a is strictly less than 0, then Bibo stability. If c times b is different from 0 and a is greater or equal than 0, then Bibo unstable. A couple of comments before running our simulations. The condition c times b different from 0, if c times b is equal to 0, it means that if b is equal to 0, it means that the input u is not entering your state at all. And if c is equal to 0, it means that your state is not affecting your output at all. So in other words, you're somehow blocking. The state is this thing that connects the input to the output, and b connects is this parameter that defines how the input is affecting the state, and c is how the state is affecting the output. Somehow you are interrupting this connection between the input to the output through the state. Instead, this parameter d is a direct connection from the input to the output. Saying that c times b is equal to 0 means somehow that the state is not really needed to determine this how the input affects the output. Still, the input can affect the output through d, but it means that that state is not really needed. So that's what the condition means. And if the state is not really needed, why are you using it? So the condition c times b different from 0, at least for first order systems, is pretty much always verified. Otherwise, you wouldn't use the state. That's what this means. So what I'm saying here as an observation is, at least for first order systems, the condition c equal to 0 or b equal to 0 is never considered, because it would mean that the state plays no role in the determination of the output from the input. In other words, we almost never consider c times b equal to 0, because otherwise the state would be useless. So we are only left really with one condition for our Bibo stability. That is, if a is strictly negative, then we have Bibo stability. If a is non-negative, instead the system is Bibo unstable. That's pretty much what the condition boils down in practice. Having said that, well, let's just get into our Simulink. So we type Simulink here, we wait until it opens, and we start with a blank model. And what I'm going to write is going to write a system of this form. While everything starts here, we're going to consider example in Simulink. And the example that we are going to consider is x dot equal to ax plus bu. And to keep things simple, we are going to consider y equal to x. So in this case, the output is the state itself. So in this case, c is automatically equal to 1. So the only thing that we are going to consider is going to be a and b. So if we go back into our Simulink browser, so we go here. If we go back in our Simulink browser, we open the Simulink browser, and as you can see, we have our library with our blocks. Since we want to write a system of this form, x dot equal to ax plus bu, we need an integrator. So let's take this model, the browser. We go into the continuous part. We take our integrator and we drag it here. Again, we are accessing some libraries. My computer is a little slow, but we are going to be happy with it. This is the integrator. And sorry, still thinking. And let's try to zoom in a bit so that you can see it better. So, okay, this should be good enough. And what else do we need? Well, typically it's very difficult to build a Simulink block without not even a sum. So let's grab a sum right away, a sum block. Let's bring it here. This is our sum. Probably, most likely, we are going to use it. And remember that I am a little old-fashioned, so we also need some special sinks. I like to use everything, send everything to the workspace, and everything to the workspace, I like to make it an array, and we also need, I like to save the times in an array as well, so I'm going to use a clock. Okay, and now if you press Ctrl E, if you remember, we have all the configuration parameters so that we can start already modifying things in the way that I like. The way that I like is that I manually save everything to the workspace. The format is just going to be an array, and I am totally happy with this. So nothing fancy for me when I'm simulating things in Simulink. I store independently all my variables in a two workspace sink, and I call the variable t. And I'm doing all this because this is how Simulink used to work many years ago when I was introduced to it, and I still do things the same way. For our integrator, we can write a comment here, and my annotation is that this is going to be my state x. Oops, sorry. This is my state x. I send my state to a variable. My variable is going to be x. Remember, I want that to be an array. Also, I like my time to be an array of times. So this is all fine. And now I have to build x dot. X dot is going to be given by the sum of an input. Let's see the equation. Is given by ax plus bu. So if I go back here in my math operations, I'd like to have a gain so that I can multiply. I can define this as variable a. Of course, Simulink is complaining because a is not defined. So here we have our, actually we can put our A variable here. I'm going to put this, and now I need another gain, and with Ctrl R I can rotate it, and I'm going to call this gain B. Okay, we have all the ingredients, we are ready. Here I need to put, I create an annotation as well. I'm going to call this quantity U. If I multiply U, that is the input of this gain B, I get BU. I sum BU and AX. So I need to grab X from here. Now I have AX, and now I have, when I'm summing BU and AX, I have AX plus BU. Everything goes into the integrator. The integrator has an initial condition that is equal to 0. That's precisely what we want. If we wanted a different initial condition, we just needed to change it. And now what do we put here for U? Fortunately, we have many possible blocks here to generate something. So, for example, I can generate a step. I take the step block here, and I move it, and this is my step. If you see, the step has a certain step time. What we have chosen is the step time is equal to 0, and the initial value is 0, but the final value is 1. So we are moving from 0 to 1, starting at time 0. So we start immediately to time 1. The block is designed so that you can start your step at any time. You can start your step at time t equal to 10, if you want to, if you prefer. But we will start with that right away. And so if we change the step with other inputs, we have our different input U, and we have a response that is not the step response. It's just the state response or the output response. State and output are the same for this simple model. And we have the variation of constants formula that is going to give us the answer. For the step, the variation of constant takes a very easy shape, and so we can simulate it. The problem is that we have these blocks here, A and B, these gains that are not defined. That's why there is this halo in red. So let's consider a case where A is negative, so we start with something stable, and B is just equal to 1. B doesn't really play a major role. So long as it's not 0, this is fine. So if we run our simulation, clicking on Run, we should have everything ready in the workspace, as you can see, ready to be plotted. And so we can plot t and x. That takes the shape. So this is, as you can see, if you say c is equal to 1, b is equal to 1, capital U is equal to 1, this is exactly the exponential of 1 minus the exponential of minus t, because a is equal to minus 1. So this is precisely what we expected. Okay, and as you can see, the system behaves well. If instead we modify a and we make a equal to 1, and we run the simulation again, and we plot it once again, we see that now the system starts from the initial condition equal to 0, and then reaches a value here that is 2.5 to multiply by 10 to the power of 4 in 10 seconds of simulation. So this system follows this exponential curve that makes it diverge. So as you can see, even though the step is a bounded input, because a is equal to 1, we have an unbounded output, verifying what we had. Now we can make b equal to 0. If b is equal to 0, let's go back to our block. Our block is actually nice. Our block b is equal to 0, so it prevents the input from entering this loop here. And so the initial condition here is 0, and so we start integrating. A times 0 is 0, we start integrating 0, so x stays equal to 0. Let's see if this is true, and we plot this, and as you can see, in this case, because b is equal to 0, the input, even though if a is positive, because b is equal to 0, still the output is bounded. Again, verifying the fact that our conditions of bounded input, bounded output stability. Let's consider another case where this time, instead of considering the step is a very special, it's a very special kind of input. Let's put an input that is going to be a little more and less predictable, because after all the step is a constant, so it's very predictable. Let's put as input, for example, this. Let's see if we can make it. No, that's not what I wanted. I wanted something. Well, the pulse generator might be fine. Let's put a pulse generator. Pulse generator is simply generating square waves. So what we are going to save u, and so the input u as well. So what we are going to do is this. We can choose the amplitude. Amplitude 1 is fine. We can have a period. Now a period of 10 is a little too long, so we go with a shorter period, and we decide that it's going to be active 25%, and then the phase delay is just to have some delay if you want that to be delayed. So I want to visualize u as well. Now u is not trivial, so I want to see it, and so I'm going to save it in my variable u, and now I'm running this again. I go back to my workspace, I remove what I had. So first of all, I want to plot t and u, and as you can see, this input tu is a square wave that is for 25% is equal to 1, and then for let me make this bigger for you, for 25% of the time is equal to 1, and for 75% of the time is equal to 0. Now you might see that this doesn't look very big square wave, and the reason is that the simulation parameters are not optimal. So this is a problem of the simulation. Let's fix it so that we are convinced that that's a legitimate square wave with an active period of 25%. So we go back and we press Ctrl E. That gives us the configuration parameters. And if you remember, I told you the last time when we used MATLAB that we wanted to have in our solver, we wanted to have in the details, we want to make this relative tolerance a little better. So I take 1 divided by at least 1 million, but in this case I'm going for the big precision. So I resimulate everything, and now I go back into Simulink, and now I plot it again. And it seems that it didn't like this again, probably because it thinks that it gets sufficient accuracy by choosing type. Let me try to force it to do it well. That is again in Ctrl E here. I'm going to choose a fixed step, and for the fixed step I'm going to choose something 0.001. So let me run this, and now I hope that solves the problem. Okay, so using this way I'm forcing the time steps to be very short, so that we have a very good time resolution of when the square wave moves from 1 to 0 and from 0 to 1. And now you can see that actually the square wave behaves like a square wave. Okay, so the input u looks like this. We have made sure that it is what we want. It's a bounded input, So now we expect to see something in the output that is bounded as well. So let's plot t and y, and t and y, t and x. And this is 0 because we forgot that b needs not to be 0, but we want b to be 1. And now I found out why the time steps were the pulse generator didn't have a good time resolution, because it was not touching the state. However, so let's plot this, let's run the simulation again with the right value of b, and let's plot it. And this happens because a is equal to 1, so that's unbounded, as we expected. Let's change a to -1, and let's redo the simulation, and let's verify that everything is bounded. So we are doing all the steps that we did before, but in reverse order. Okay, as you can see, this is the response that you get when you give a square wave to your stable system with a equal to -1, b equal to 1. Maybe you are not convinced that this is actually bounded, so we might decide to have a longer simulation, and this is the last change that we're going to make. So instead of simulating for 10 seconds, we're going to simulate it for 100 seconds. Once the simulation is done, we are ready to plot this. And now let me enlarge this. As you can see, what you're going to get is a sequence that is periodic. That's an important thing. But the most important thing for what we have seen is that this sequence is actually bounded. And if we can zoom in, we see that this is what the state and the output response are going to look like.